this module, we will model electrical systems. Specifically, we will determine mathematical models, both differential equations and transfer functions, that capture the dynamic behavior of electrical systems like circuits. As you might imagine, electrical systems are very important for electric vehicles, and one such application that's specific or specifically important to electric vehicles are power electronics, which we will discuss in this section. Two quantities that are very important for understanding electrical systems are voltage and current. So voltage is a measure of the force that causes electrons to move through a circuit. We will use the letter E to represent voltage, representing sort of a mechanical interpretation of voltage, i.e. it is also called the electromotive force. And so in one sense you can think of voltage as the relative strength of an electric force field that causes electrons to move through a circuit, either repelling or attracting the electrons. And as such, what matters with voltage is its relative strength. So if we talk about the voltage at this point in the circuit being 3 volts, really what we're saying is that it's 3 volts more than some ground reference, where ground is what we've defined to be 0 volts, and that's often represented with this symbol. And so again, when we're talking about a circuit, what we really care about is the difference in voltage between two points in the circuit. So in this case, on either side of this circuit element, the potential difference is 3 volts. And it doesn't really matter if we're saying that the one side is 3 volts and the other side is 0 volts, or if we're saying that the one side is at 10 volts and the other side is at 7 volts. If you're more comfortable thinking about mechanical systems, you can think of voltage as sort of a height or a pressure differential, and the electrons flowing through the circuit as water. So if you think of a pipe or some other sort of fluid system, water is going to flow downhill. It's going to flow from a higher elevation to a lower elevation, or it's going to flow from high pressure to low pressure. And in the same sense that voltage is a potential difference, it's the same concept with elevation and pressure. If we're talking about elevation, it's with reference to some ground, like we would say we're a certain height above sea level. Or if we're talking about pressure, again we would talk about it with respect to some reference, i.e. we would say that it's either atmospheric pressure, so that's the pressure relative to the pressure of the atmosphere, or we would say it's absolute pressure, it's the pressure relative to a vacuum. Another important quantity that we need to understand is current. And current, which we will represent with the letter I, is a measure of the rate of flow of charge through a circuit, i.e. the rate of flow of electrons. And so again, we can think of this just like a mechanical system. You can think of the electrons flowing through the circuit like water flowing through a pipe. Here, charge is represented with the variable Q, and so current is the rate of change of charge with respect to time, or the flow of charge with respect to time. With these circuit elements, we will make the assumption of the idea that charge is conserved, so that whatever charge or however much current is flowing into a node is equal to the amount of current flowing out of the node. When we discuss electrical systems and model them, we will consider 3 basic types of elements: resistance elements, capacitance elements, and inductance elements. And just as was the case with mechanical systems, where we talked about spring elements and damper elements, we don't literally mean resistors and capacitors. We could have a piece of wire and we can talk about its capacitance properties or its inductance properties. While these are the basic sort of elements that we're going to analyze when we build up and model electrical systems, there are other elements like diodes and transistors, etc. For our purposes, we're not going to get into too much detail with those elements. We will treat them sort of as idealized elements and won't study their dynamic behavior. The simplest type of element to consider is a resistance element. We will represent resistors with the symbol shown here. If you think back to your earlier undergraduate days, you might be able to remember the relationship between the voltage across a resistor and the current through the resistor. That relationship is called Ohm's law. It's a linear relationship. It says that the voltage across a resistor is equal to the current through the resistor times the resistance. So resistance is basically the ratio between the voltage across and the current through. Resistors dissipate energy much like a damper does in mechanical systems, and resistance is measured with units of ohms. The next type of element that we will consider is a capacitor or capacitance element, which is slightly more complicated than a resistor. Capacitance is measured as the charge stored per unit voltage, as shown here. So again, Q is charge, E is the voltage across the capacitor. What this means makes a little bit more sense if we think about physically what a capacitor is. So this symbol represents the simplest sort of structure or construction of a capacitor. You can think of a capacitor as consisting of two conductive plates with some dielectric material in between. And so the idea is that as electrons flow through the circuit, the electrons build up on one side or on one of these plates. And that buildup of charge creates an electric field, which then pushes electrons off the other plate. So in reality, a current doesn't flow through the capacitor, but that's how we will model it. In reality, what happens is that electrons build up on one side and displace electrons off the other side. So it sort of appears, if you looked at it as a black box, as if current was flowing straight through. As this charge is built up, in essence, it's that capacitor is storing energy. So we can think of a capacitor as a spring. It stores potential energy, and that built-up charge can then be released later on. This fact makes capacitors have many applications, and one application within hybrid electric vehicles is that they can be used to store energy like a battery. Specifically, sometimes what are called ultracapacitors, which are just very large capacitors, are used as a way to temporarily store electrical energy that's being generated. Looking at this relationship, if we think back to the fact that current is the time rate of change of charge, we can get a relationship between the voltage across the capacitor and the current through it. Rearranging, we can multiply the voltage to the left-hand side, divide through by the capacitance. So we have this relationship. Up here, we have that current is the time derivative of charge. The inverse of a derivative is an integral, and so we can, in essence, multiply dt to the other side, and we can integrate both sides to get an integral expression of current in place of charge. This expression is what we will use for modeling capacitors, and it also gives some intuition. An integral is basically a sum. It's an accumulator. So as current flows into the capacitor, it sums up and builds up charge. And so if we wanted to think about a capacitor using our same sort of fluid analogy, you can think of a capacitor as an accumulator. It's a reservoir that sort of stores the fluid, which then can be released at a later date. Capacitance has units of farads. Our final element that we will consider are inductance elements, or inductors. Again, just has the symbol for a capacitor represented its mechanical construction. The symbol for an inductor also represents its mechanical construction, or at least in its simplest form. This symbol represents a coil of wire. And so the way that an inductor works is that as the current flows through this coil, it induces a magnetic field. And changes in the current creates a corresponding change in the magnetic field, which generates a voltage or an electromotive force that opposes this change in current. So in other words, the voltage across an inductor is proportional to the rate of change of the current through the inductor. In this sense, inductors can be thought of as inertias. Again, going back to our mechanical analogies, the fact that this magnetic field is inducing a voltage that opposes the change in current, it's like a mechanical inertia. Inertia can be thought of as a measure of a mechanical system's resistance to change. An object in motion tends to stay in motion. An object at rest tends to stay at rest, where that tendency is its mass or its inertia. The same thing with inductance. The voltage is induced to sort of oppose changes in current. And just as we learned that inertia store kinetic energy, so do inductors, where they store it in terms of an electrical field or a magnetic field. The units that we will use for describing inductance, or the amount of inductance, are henries. We will now discuss briefly how to analyze resistors in series and resistors in parallel. This is important in general for analyzing circuits with resistors in it, but this is also something that will prove important later on in this module when we discuss impedance. So when we discuss impedance, what we learn here about resistors in series and in parallel will be helpful for analyzing inductors in series and parallel and capacitors in series and parallel also. Looking at this simple circuit of 3 resistors in series, in essence we want to replace them by a single equivalent resistance. So we want to simplify our circuit by replacing these 3 resistors by a single resistor, or a single equivalent resistor. Looking or recalling what voltage is, the voltage across each resistor, so the voltage across the first resistor is E1, across the second resistor is E2, and across the third resistor is E3. And the current through all 3 resistors is the same, because in essence the electrons have only a single path to go through. And since charge is conserved, however much current is flowing through the first resistor must also flow through the subsequent resistors. And since voltage is a potential difference, the total voltage difference across all 3 resistors is just the sum of the voltages across the individual resistors. If there's 3 volts across the first resistor, 2 across the second, and 1 across the third, then the total potential is just going to be the sum of those potential differences. Applying Ohm's law to each resistor individually, recall that voltage across the resistor is equal to current through the resistor times the resistance, where again all 3 resistors have the same current I. So E1 is equal to I times R1, E2 is equal to I times R2, and E3 is equal to I times R3. The fact that the currents are all equal means that we can factor them out, and then we can represent this equivalent resistance as the voltage across all three resistors divided by the current through all three resistors. So using this Ohm's law again, we can divide this I to the left-hand side, and we get that the equivalent resistance is E divided by I, which is equal to the resistances summed together. So in summary, the equivalent resistance of resistors in series is just the sum of the individual resistances. Now we will discuss resistors in parallel. Since voltage is a potential difference and all three resistors are connected together at the same node on the left-hand side and the same node on the right-hand side, the potential differences across all three resistors is equal, and we will define that to be E. The current through the individual resistors, however, can be different. So you can sort of imagine, that we have electrons flowing through here, and each of the electrons can choose a different path. So some of the electrons will flow through the first resistor, some of the electrons will flow through the second resistor, and some of the electrons will flow through the third resistor. Looking at trying to quantify how much current is flowing through each resistor, we can again use Ohm's law. Using the fact that current is conserved, however much current is flowing into this node will equal however much current is flowing out of it. The current in is going to equal I1 plus I2 plus I3. Using Ohm's law, each of those currents is equal to the voltage across the resistor divided by the corresponding resistance. And intuitively, you can think of this as the current wanting to take the path of least resistance. So the smaller the resistance, the more current is going to flow through that path. Since each of those voltages are equal, we can factor that out front, and then again capturing this as an equivalent resistance. Resistance is voltage divided by current, so we can divide I to the right hand side, and then we can take this sum of resistances, divide it to the left hand side, and we get that the equivalent resistance is equal to this final expression. We can also do a little bit of mathematical manipulation, and it can be shown that this is also equal to the ratio R1 times R2 times R3 divided by R2 times R3 plus R1 times R3 plus R1 times R2. Again, representing or understanding how to reduce resistors in series and resistors in parallel will be helpful when we discuss impedances later in this module. At this point, we will now introduce some laws for deriving the differential equations for electrical circuits from first principles. And so much in the same way that we did with mechanical systems where we applied Newton's laws, here we will apply Kirchhoff's laws. The first law that we will learn is called Kirchhoff's current law, or also called the node law. And what it says is that current into a node is conserved. So if we're considering a node in our circuit, this node does not accumulate any charge. Whatever current is flowing in must exactly equal the amount of current flowing out. And so mathematically we could say it as this way, I1 plus I3, the current into the node, is equal to I2 plus I4 plus I5, the current out of the node. And this is a notion that we've already sort of talked about a little bit. The second law that we'll use is called Kirchhoff's voltage law, or the loop law. And what it says is that voltages around a loop must sum to zero. And this makes intuitive sense because voltage is a potential difference. So if we're at the same place in a circuit, then we must have the same voltage or the same potential. For example, if we start at this point in our circuit and we move around the circuit where we're assuming that current flows in this direction, i.e. current flows clockwise around the circuit, if we define this to be our ground or to be 0 volts, as we go across this symbol here, this is a voltage source or a battery, and so this causes a jump in voltage of E volts. As we continue around the circuit, when we go across the resistor, we will drop voltage according to Ohm's law. And so, if this is the positive side and that's the negative side, we'll have a voltage drop of IR. Then we continue. The voltage that drops across the inductor is proportional to the rate of change of the current. So the drop in voltage will be equal to L times di dt. And then finally, we go across the capacitor. And so the drop across that capacitor is proportional to 1 over C and the integral of the current, or the amount of charge that's accumulated in the capacitor. At this point, we're back to where we started, and so the total change in voltage should be 0. If we were to write this as an equation, it would look like this. So as we go across, we have an increase in voltage of E, then we drop across the resistor, then we drop across the inductor, and then we drop across the capacitor, and the total sum should be 0 since we're back to where we began. Here's an example of a more complicated circuit with 2 loops, and we're going to derive the governing equations for this circuit. There are different approaches that one can take. In particular, one could use the node law, or one could use the loop law. In general, we will use the loop law. So instead of sort of picking a few nodes to look at in this circuit, we're going to look at the different loops. In this case, we will end up with one equation for each loop. And what we will do is we will assume a direction for the current. We may not know for sure which direction current is flowing through a particular loop, but if it turns out that we guessed incorrectly and we actually attempted to solve for the current and the current came out to be negative, then we would know that it's opposite the direction we assumed. So here's our first loop. I will assume that it flows clockwise, and I'll call the current I1. And then here's our second loop. Again, I will assume that it flows clockwise, and I will call that current I2. And then we will apply the loop law to each loop individually. Okay, so we'll start with loop 1. And I'll pick a point in the circuit to start from. As we go around the circuit, first I'll come across this voltage source, which has a potential EI. And so if I'm assuming that this is sort of ground, we will have an increase in voltage of EI. Then when I come across this resistor, I'll drop across this resistor according to Ohm's law. So I'll have a drop equal to the current times the resistance. Then I will drop across this inductor, where the drop across the inductor is proportional to the rate of change of the current. This branch is slightly different, however, because not only have I defined a current I1, which is flowing down through the inductor, I've also defined a current I2 which is flowing up through the inductor. And so I will also need to include the drop due to I2. And since it's flowing in the opposite direction, it will have a sign that's the opposite of the sign for current I1. Then we drop across this resistor, where again we have I1 flowing down through the resistor and I2 flowing up through the resistor. So I1 minus I2. At this point, we've completed our circuit around the loop, and that whole thing must sum to 0. We'll then apply the same approach for modeling loop 2. If I begin at this point and I start to flow around the circuit in the direction I've defined I2, the first element I will come across is the capacitor. And the drop across the capacitor, so it's negative since it's a drop across that element, it's proportional to 1 over C times the integral of the current, where the only current that's flowing through this element is I2. This little symbol here is a little bit different than the symbol I've been using, in the sense that we only have one flat plate and then we have a curved plate. This symbol represents what's called an electrolytic capacitor. And so some capacitors, the orientation doesn't matter. You can insert a capacitor either way into a circuit. With an electrolytic capacitor, the direction matters. And so you need to insert an electrolytic capacitor in a particular direction so that current flows in the correct direction through the capacitor, otherwise it will be damaged. This is something that we won't get into any great detail, but I just wanted to point this out in case you had a question about the difference in symbols. So again, I started here where I defined this to be ground, or R0. We dropped across the capacitor, then we continue around the loop and we'll drop across the resistor R2. Where again, in this case, I have I2 flowing up through the resistor and I1 flowing down through the resistor. And then I go through the inductor, where the drop is proportional to the rate of change. At which point I'm back to where I began, and so everything should sum to 0. Therefore, we're done. These two equations govern or model the dynamic behavior of this circuit. One thing that you'll notice here is that these aren't strictly differential equations, in the sense that they also include integrals. So they're integral differential equations. Sometimes people feel more at ease if everything is written as a differential equation. And so one way to accomplish that is to rewrite the equations in terms of the charge Q. So these were the equations that we derived on the previous slide. And we're going to rewrite them in terms of charge, where, if you recall, current is the time rate of change of charge. So looking at the first loop equation, the E1 stays the same. Current is the time rate of change of charge, so we can just replace this I1 by Q1 dot. Here we have the first derivative of current. Since current is the first derivative of charge, this is taking another derivative, and so this is equal to Q1 double dot, the second derivative of charge, and this is equal to Q2 double dot. And then again, this is current, which is Q1 dot, and this is I2, which is Q2 dot. So if we insert all of those substitutions, this is the resulting differential equation. We can do the same thing for loop 2. So here I2 is equal to Q2 dot. If we integrate Q2 dot, we may recall that integrals and derivatives are inverses of one another, inverse operations. So if you integrate a derivative, the integral and the differentiation in essence cancel out. So if I integrate Q2 dot, I'm going to get back just Q2. Here again, I2 is Q2 dot, I1 is Q1 dot, then I differentiate Q2 dot to get Q2 double dot, and I differentiate Q1 dot to get Q1 double dot. And so this is the equation for the second loop. In this case, the Q2 has a very physical meaning. So Q2, if we recall, this is I1 was the current through the first loop, I2 was the current through the second loop. So since I2 is the current through the capacitor, Q2 is the charge built up on this capacitor. So that has a very straightforward physical meaning. Q1 does not have a corresponding physical meaning in this circuit. There is no place that charge accumulates or builds up in this loop, but we will just use it as, we will write it anyways, just as a mathematical substitution. Looking at these two equations, we in essence have second order differential equations, which has a similar form to the mass spring damper equations that we derived previously. As such, all of the approaches that we used for solving a mechanical differential equation is exactly the same as the approaches we would use for solving an electrical differential equation. At this point, the differential equations are the same, they just represent different things physically. In general, a mechanical analog exists for each electrical circuit, and so this can be something, if you're a mechanical engineer, to maybe help you better understand electrical circuits. So for example, resistors dissipate energy like a damper, so resistance is equivalent to a damping coefficient, B. Inductors behave like inertias, so inductance is equivalent to mass, or rotational inertia. Capacitance, or capacitors, store potential energy like a spring, so 1 over C is similar to a spring constant, or the stiffness in a mechanical system. Voltage is like a force in a mechanical system, and charge is like a mechanical displacement, meaning current is like a velocity. There are many examples of electric circuits in electric vehicles, as you might imagine. One important example that we will discuss here as a motivating sort of reason why we would want to be able to model and analyze circuits are the power electronics in the vehicle. In particular, we will look at DC to DC converters. DC stands for direct current, and it represents circuits where the voltage is constant, i.e. Voltage from a battery or some source like that. A DC to DC converter, in essence, tries to change the level of the DC voltage. It tries to raise the voltage from a DC source or lower the voltage from a DC source, or at least approximately or on average. One such example for where this is necessary is in charging a battery. in general, in order to charge a battery, the voltage being applied to the battery needs to be higher or larger than the open circuit voltage of the battery. If we had a situation where we had a braking event, we have regenerative braking that's driving a generator, which is in turn generating voltage, we wouldn't be able to charge the battery for small braking events because the voltage would be too low. But what we can do is we can use a step up or a boost converter in order to increase the voltage, step the voltage from the generator up to a high enough level that it can actually charge the battery. Another example of where a boost converter could be used is it enables the electric motor, the traction motor in an electric vehicle, which tends to be high voltage, to be powered by a lower voltage battery. This ability, having a lower voltage battery, allows the battery to be smaller and lighter. And then its output is just stepped up using a boost converter to a sufficient level that it could actually drive the electric motor. As a very basic or rough intro to how a boost converter works, here's a picture. The idea again is we have some supply voltage, and this boost converter, which is in between, we're going to use to increase the voltage, the supply voltage, to a level such that the voltage across the battery is on average sufficiently high that we can actually charge the battery. And so the way that it works is that we close this switch, and when we do that, the current flows through the circuit in this manner. We call this sort of the on state, when the switch is on or closed. And as it does that, as the current is flowing through the inductor like this, the energy stored in the inductor increases. When the switch is then opened, this is an open circuit and current can't flow this direction any longer. And so the current flows through the outer loop. So this is called the off state, when the switch is off or the switch is open. By controlling, and when that is done, the energy that's been stored in the inductor is then released. And by opening and closing this switch, we can in essence change the average voltage across the battery in order to step it up in essence. Another application of where a DC to DC converter could be used is to enable low voltage appliances like pumps and fans and things to be driven by a high voltage battery, i.e. the battery used for driving the traction motor in an electric vehicle. And so since the accessories are very low voltage and the traction battery is very high voltage, we need what we call a step down or a buck converter in order to lower the voltage. The way that this converter roughly works is that, again, we have similar sort of structure with a switch. You close the switch. When you do that, this diode is reverse biased, so current doesn't flow that direction. It's unable to flow that direction. So the current flows through the outer loop through the accessory. And this is called, this is the on state. Energy is increasing, is being stored in this inductor. When the switch is then opened again, the supply is in essence disconnected from the accessory. So no current comes from the supply any longer. And what happens is that current just cycles in this inner loop. And again, by changing the way that the switch is opened and closed, we can make the voltage across the accessory be on average at a lower voltage than the supply voltage. So these are some very rough introduction. At this point we will go ahead and choose the boost converter and analyze it in more detail. So here's a boost converter where we've removed the capacitor that was here. I'll explain a little bit better what the purpose of that capacitor was, but it was, in essence, it was there as a filter. But we will analyze this boost converter from first principles, so using Kirchhoff's laws and things like that that we just learned. In the process of doing this, we will make some pretty big simplifying assumptions, but it will help to give us a sense of why this converter works the way it does. If you take another class like a power electronics class, you will get into much greater detail, and you won't necessarily analyze it from first principles. In particular, there's often some sort of tricks done where you're able to basically look at the circuit in steady state and sort of make some assumptions about how the behavior in the on state and the off state are sort of averaged over. You also will get into more detail, the effect of the capacitor here, the effect looking at the actual behavior of a diode, looking at how this switching is done with transistors, looking at sort of the efficiency of the process and all these other sort of details. But what we're going to do right now is just look at the system sort of from a simplified first principles point of view. So initially, we'll assume that the switch is initially closed. When we close that switch, this transistor acts like a perfect switch, and so in essence there's no resistance in this path. And so the current is going to take the path of least resistance. It's going to take this path as opposed to going through the load, and the current will cycle in this loop, increasing the energy stored in the inductor. And so in this state, we want to find the current in that loop, in that inductor, assuming that initially there was no current flowing through the circuit. The way that we do this is first we generate the governing differential equation for that circuit. We can use Kirchhoff's loop law as we learned previously. If I start at this point in the circuit, as I go around the loop in the direction that I've drawn I first come across the supply, which causes an increase in voltage by the amount V supply. And as I continue, I drop voltage across the inductor, where the drop, if you recall, is proportional to the inductance multiplying the time rate of change of current. And then continuing along, I return back to the position, the location where I started, and so that total change in voltage around the loop is equal to 0. So this is the governing equation, very simple equation. I had a bump in voltage across the supply, then I drop across the inductor, and then I'm back to where I started. In order to find I of t, in essence, I just want to solve this differential equation. If you think back to how we've learned how to solve differential equations, the way that we do that is employing the Laplace transform. So we're going to go ahead and take the Laplace transform of this differential equation. When we do that, V supply we'll treat as a constant, E voltage. The Laplace transform of a constant, in essence, we treat like a unit step. One way to think about it is that initially, let's say the power supply is turned off at time t equals 0, you flip it on, and so it behaves like a step. So if we do that, the Laplace transform of a constant or a step will just be E over S. Then we'll have the Laplace transform of this quantity. The L is a constant, so it just comes out front. we can look up in our table and recall that differentiation in the time domain becomes multiplication by s in the Laplace domain. So this is the Laplace transform of the first term, this is the Laplace transform of the second term, where differentiation becomes multiplication by s. We also have this extra term due to the initial condition, but for this case we were told to assume that the current was initially 0, so that will drop out. Once we've taken the Laplace transform, the next thing that we would like to do is then to solve for I of s. We will solve the algebraic equation. And so this negative term here we can add to the right hand side. To get I of s by itself, we can divide through by s times L. As I do that, you end up with E divided by L, and then 1 divided by s times s. So that gives us an expression for I of s. And then finally, as it's desired for us to find I of t, the last thing to do is then to just take the inverse Laplace transform. E over L is just a constant that comes out front. If we look in our tables again, the inverse Laplace transform of 1 over s squared is t. It's the unit ramp. So that's what I of t is equal to, and we make the presumption that this function begins at time t equals 0. So, presuming that the current starts at 0, when the system is turned on and the switch is initially closed, the current through the inductor, or the current in this loop, will behave according to this equation. This is a simplification in the sense that we're assuming a perfect switch, an idealized switch, and we're neglecting the resistance in this length of wire, but it's a reasonable approximation. Next, we want to look at what happens when the switch is then opened again. So when the switch is opened, the diode is forward biased, and the current flows outside the loop because it can't flow through this middle branch any longer because the switch is open. So what we want to do is we want to find I of t, in this case, in the off state when the switch is open. But now we can't assume that the current is initially 0 because current was already flowing. Initially the switch was closed, current was flowing through here, energy was building up in the inductor, and so when the switch is opened, there was already current flowing in the circuit. So we can't make the same assumption we did in the previous case. The approach that we'll use for finding I of t is basically the same as we did in the on case though. First, we will find the governing equation for this circuit. We start at some point in our circuit as we go across the voltage source. We step up in voltage, V supply. We then drop across the inductor in the same manner that we did previously, with a drop equal to L di dt. And then we drop across the load according to Ohm's law, I times R load. Then we're back to where we began, and the total change in voltage around the loop is 0. So this is the governing equation that describes the current flow through this circuit. We want to solve this differential equation to find I of t. Follow the same process. First we take the Laplace transform. This is just a constant, so it becomes E over S. This has the same form it did in the previous case, where the Laplace transform of the time derivative will be S times I of S minus I of 0. And when we take the Laplace transform of this term, R load is just a constant. The Laplace transform of I of t will become I of S. So this is the Laplace transform of that differential equation, where again we can no longer assume that the current is initially 0. The value of this is whatever the current was at the time that the switch was opened. Once we've taken the Laplace transform, the next step that we want to perform is to solve for I of S. So got two terms with I of s. We have this term, we have this term. This negative sign will become positive if we add R load times I of s to the right hand side. If I distribute this negative L, I'll have negative L times S times I of s. That again becomes positive when I move it to the right hand side. You can then factor out an I of s from those two terms. So you're left with E over S on the left. You're left with L times I of O, where the negative multiplying a negative becomes a positive. On the other side, we can factor out the I of s. So I of s multiplies the quantity S times L plus R load. And then to finish solving for I of s, we simply divide through by the quantity S times L plus R load. And that gives us this expression for I of s. Once we have I of s, the last step is then to take the inverse Laplace transform. This term is relatively simple. We have a constant, and then we have a constant times s plus another constant. So this has the basic form of 1 over s plus a if you rearrange it. And so this is something that with a little manipulation we can find directly in our Laplace transform table. This term, depending on how large our Laplace transform table is, we may not be able to find it directly in the table. And so what we need to do is we need to split this into two terms using what we call the partial fraction expansion. Okay. In the previous modules, we performed the partial fraction expansion using MATLAB. In this case, we will go ahead and perform it by hand. Looking at this, we basically have two terms in the denominator, just s, a pole of 0, and then we have a non-zero pole. So we have two poles that are distinct and real. And if you think back to the three different cases, think about which case this applies to, case 1, case 2, or case 3. Since this example rational function has two distinct poles that are real, the coefficients or the residues in the numerators will just be simple constants. So here we have two terms in the denominator. We can split them into two different terms, one for the s and one for the quantity SL plus R load. And so at this point what we want to do is, in essence, we want to be able to solve for A and B. And the way that we're going to do that by hand is just doing some algebra. In order to compare these two terms to the term on the left, we need to do the opposite of what we just did. We need to actually find a common denominator. So in order to combine these two, we need them both to have a denominator of S times the quantity SL plus R load, so that we can combine them as such. In order to make this term have the denominator we desire, we need to multiply the top by S and the bottom by S. Multiplying and dividing by S is equivalent to multiplying by 1, which doesn't change the value of this quantity. In order to make this term have the correct denominator, we need to multiply and divide by the quantity SL plus R load. If we do that, then both terms have the same denominator and we can combine them. So what we'll have is A times the quantity SL plus R load plus B times S, giving us this expression. Looking at the expression we have on the left and the expression we have on the right, the denominators are the same and the entire quantities are equal. Therefore, the numerators must also be equal. Looking at this, we in essence have one equation but two unknowns, since we don't know A and we don't know B. So we have E is equal to, if I distribute the A, plus B times S. But even though it appears that we have one equation and two unknowns, in actuality we actually have two equations, since looking at the left and the right, all of the S terms must be equal and all of the constant terms must be equal. So looking at just the S terms, on the right hand or on the left hand side we have no S terms. So it's as if the coefficient for the S term is 0. On the right hand side we have an S term with a coefficient of A times L and an S term with a coefficient of B. Therefore, on the left, 0 must equal A times L plus B. We can do a similar thing for the constant terms. S to the 0 is equal to 1, and so this can be thought of as our constant terms. On the left, we have a constant term of E. On the right, we have a constant term of A times R load. If we had a higher order numerator with S squared terms or S cubed terms, then we could also match those coefficients on the left and the right hand side. So looking at this expression, we can solve for our first coefficient A, just dividing through by R load. We get that A is equal to E divided by R load. We can then use the first equation to find B, where if we subtract A times L to the other side, we get that B is equal to negative A times L, and then we can substitute this expression for A, and we get that B is equal to negative E times L divided by R load. So that completes the partial fraction expansion. That's how we solve for the coefficients A and B. Once we plug those back into our expression for I of S, we can do the inverse Laplace transform to get I of t. So this is I of t. This is our expression for I of S from the previous slide, where this is A over S, and this is B over SL plus R load, and then this was the final term from the previous slide. Taking the inverse Laplace transform of the first term is relatively simple. This is just a constant over S, so it's like a step. The second term looks similar to an expression of 1 over S plus A, except we need to get rid of this L. So in essence what we need to do is we need to divide through by L in the denominator and the numerator, and by doing that we'll get a denominator of S plus a constant. Same thing with this term. We need to divide through by L in the numerator and divide through by L in the denominator. Doing that, this L cancels out. We have to distribute, so this R load ends up with being divided by L. In the numerator, that L cancels out. Over on this term, this L cancels that L, this L cancels that L, and we again end up with a plus R load divided by L. So again, this is just a constant times a unit step. This is a constant over S plus A, where the inverse Laplace transform of 1 over S plus A, if we recall, is e to the minus AT, where this is what A is equal to. And if you don't remember that property, you can always look back in your Laplace transform table. Here will also be the same sort of form, S plus A, where this is A, so we will get an e to the minus AT. It's just that the constant's different. So performing that inverse Laplace transform, here's our e to the minus AT multiplying a constant, here's our e to the minus AT multiplying a constant. This is a step, but since we don't consider our function to begin until t equals 0, we can also just write it as a constant starting at t equals 0. So this is the behavior of the current through our circuit or through the inductor once the switch is opened. So when the switch was closed, the current increased linearly. That's what we found 2 slides ago. and then once the switch is opened, it then will behave sort of as a decaying exponential. So there's some constant term, and then there's a decaying exponential where the rate at which it decays depends on the resistance of the load and the amount of inductance. So let's go ahead and look at what the graph of the current through the inductor looks like. So if we recall, when the switch was on, the current increased linearly according to this equation. That's what we found. It increases basically with a slope of E over L. Once the switch is turned off, then the current behaves according to this equation, where this is what the current, on the previous slide this was called I.O., but in essence this is the current at the point at which the switch is opened. So when the switch is closed, the current increases, and then once the switch is opened, the current then behaves according to this equation, where it will decay. At the point that t is equal to Ts, this becomes 0, and e to the 0 is 1. So what we will have is that this term will cancel that term, and the current is just equal to I of t of s, which is what we would expect the current at the instant when the switch was turned. As t goes to infinity, this exponential will decay to 0, and so this whole term will go to 0, and the current will approach E over R load, and it'll behave in essence like this. So when the switch is closed, current increases, and then when the switch is opened, it will decay. This is making the presumption that that we waited until the current was greater than E divided by R load before we flipped the switch. The way that this boost converter works is to continue to switch the switch on and off in order to achieve an output voltage at the level that we desire. So if we continue to do that, we get this sort of behavior. So the switch here is closed, the current flows in the inner loop, causing the energy stored in the inductor to increase. When the switch is opened, this becomes an open circuit, current won't flow that way. The diode is reverse biased, so the current flows out that way. In this graph, we've sort of exaggerated the ripple in the current. In reality, the frequency with which the switching between the on and the off state is done will be much higher. So there will be ripple, but it will be pretty small magnitude ripple. And so this DC to DC converter doesn't exactly achieve a perfect DC output, but it's a DC output within a reasonable approximation. So this graph is the graph of the current through the inductor. Ultimately, what we're trying to do, though, is we're trying to affect the voltage across the load. And so when the switch is on, in essence, the load is disconnected, so no current flows through the load at all. So this is really what the current through the load looks like. When the switch is on, all the current goes through the switch and none of it goes through the load. Obviously, this isn't the sort of behavior that we want. We're trying to achieve a DC voltage at the load. And so the way that that is achieved in reality is with the addition of the capacitor. So the idea is that when the switch is when the switch is on, there is still current flowing through the load, and where that current comes from is from the capacitor. So the capacitor stores charge, stores energy, which is then released when the switch is flipped. And so in reality, we'll get a much smoother looking kind of output. In practice, the DC voltage, the level of boost that's achieved, is affected by, one way to affect it is by changing the frequency. In reality, the way that these are operated is generally the frequency is kept constant, and what's changed is the duty cycle. That is, the percentage of time that the switch is on or the switch is closed as compared to the total period. Using a higher frequency gives us a smoother output, but at the cost of greater efficiency losses. Every time you switch the transistor, there are efficiency losses. And in practice, the output is smoothed by using a capacitor, which acts like a low-pass filter. And so we're sort of just glossing over some of these practical considerations, but if you take a course in power electronics, you will get to understand these elements in much greater detail. So far in this module, we've been modeling electrical circuits as differential equations. If you recall, an alternative mathematical model is a transfer function. So an alternative approach is to model the circuit directly in the Laplace domain. When we do that, we will use something called complex impedance. Impedance is a similar concept to resistance, and for resistors, impedance and resistance are the same. For capacitors and inductors, however, impedance changes with frequency, and so that's why it's a more complicated concept that's needed. We can't really speak about the simple resistance of an inductor or a capacitor. The frequency dependence of this quantity won't make a lot of sense to us now, but it's something that we'll try and come back to later in the semester. In this analysis, we can treat complex impedances like we did resistances previously, and the reason that we can do that is the definition of impedance has a similar relationship to Ohm's law. So whereas resistance was voltage divided by current, impedance is also voltage divided by current, except here there's the voltage and the current aren't constants, they are dependent on frequency. Because of this adherence to an Ohm's-like law, we can also combine the impedances of components in series and in parallel the same way that we generated equivalent resistances of resistors in series and parallel. So now we want to define what the impedance of our three different components are. So starting with resistors, we'll take the Laplace transform of Ohm's law, the time-based relationship between voltage and current. E becomes E of S, I becomes I of S. R is just a constant, so it comes out front. Complex impedance is voltage divided by current, which in this case, if we take this current and divide it to the left-hand side, we will find that impedance is just equal to resistance. Therefore, the impedance of a resistor is equal to R. Now we will do the same thing for capacitors. Recalling the relationship between voltage across a capacitor and current through a capacitor, we have this integral-based relationship. Recall our Laplace transform property that states that integration in the time domain becomes division by S in the Laplace domain. Therefore, we have this expression E of S equals 1 over C times I of S over S. Again, to get the impedance, we need to divide through by I of S. And then we get the complex impedance of a capacitor is equal to 1 over C times S. Finally, we perform the same sort of action for an inductor. Voltage is equal to inductance times the time rate of change of current. Recall the property that differentiation in the time domain becomes multiplication by s in the Laplace domain. We divide through by I of s to get that complex impedance is equal to s times L. So in essence, we just need to memorize these three sort of properties, or these three definitions of complex impedances for our three different types of components. But also keep in mind that we're implicitly assuming something when we did this. And what we're assuming is that the initial conditions are zero. So when we took the Laplace transform of this derivative, we're basically assuming that the current through the inductor was initially zero. And when we took the Laplace transform of this integral, we're basically assuming that the initial value of the integral was zero. That is, there was no initial charge on the capacitor. So here's a circuit that we addressed earlier that we found the governing differential equations for. We found one equation for each loop. From those differential equations, we could find the transfer function EO of s divided by EI of s. And the way that we do that is we take the Laplace transform of the differential equations and then do some algebra in order to get it into the form output over input. That process would actually be somewhat tedious, the algebra involved. It's actually much simpler to derive the differential equation directly using complex impedances, and so we'll go ahead and demonstrate that approach here. So the first thing we need to recognize is what are the complex impedances of the individual components. So if you recall, the complex impedance of a resistance, of a resistor, is just its resistance. So the impedance of this resistor is just R1. Recall what the complex impedance of an inductor is. You can look back on the previous slide, but it's equal to S times L. Then this resistor again, impedance is equal to resistance. And then finally we have the impedance of the capacitor, where again, if you look back on the previous slide, you can see that the impedance is equal to 1 over C times S. We then want to simplify this, and we can use these properties of how to reduce or how to find the equivalence of components in series and in parallel. We'll go ahead and define this resistor to be Z1, have impedance Z1. These two components, the inductor and the resistor R2, are in series. And so if we recall back to how to combine resistors in series, you recall that the resistance is sum. So using that same idea, the impedance is sum. So the impedance of this branch with these two components in series is SL R2. We can then notice that this branch is in parallel with this branch. And if we recall, the equivalent resistance of two resistors in parallel is their each individual resistance, the inverse of each individual resistance summed together, and then the inverse of that complete sum. So I will call the equivalent impedance of these two branches in parallel Z2. We'll have 1 over the impedance of the first branch, which is those components in series, which we found to be SL plus R2. And then we'll add that to the inverse of the impedance of the capacitor, the other branch, whose impedance is 1 over CS. And then that total is also inverted. If we're dividing by a fraction, you may remember that that's the same as multiplying by its reciprocal. So the reciprocal of 1 over CS is CS. In order to combine these two inner elements, they need to have a common denominator. So in order to combine them, we need them both to have a denominator of SL plus R2. In order to achieve that, we need to multiply CS by SL plus R2 and divide it by SL plus R2. Once they have a common denominator, then we can just add the numerators. So the denominator is SL plus R2. The numerator is 1 plus, if I go ahead and distribute, I get C L S squared plus C R2S and then if I invert that, I get that Z2 is equal to SL plus R2 divided by CL S squared plus C R2S plus 1. So we've taken a relatively complex circuit and simplified it into the form that I'm going to show you on the next slide, where I have a single impedance Z1 in this location and a single impedance Z2 in this location. If you look at this, you may recognize it as having the form of a voltage divider. And a voltage divider is much simpler, and we can determine a transfer function for this simpler equation, this simpler circuit. I'm going to make the assumption that the current is equal to I and it flows clockwise around the circuit. If you recall, a transfer function that we're trying to find is EO of S divided by EI of S. It's basically the Laplace transform of the output divided by the Laplace transform of the input. If we look at EO, the voltage EO, it's the voltage across Z2, where the current through Z2 is I. Thinking back to the definition of complex impedance, voltage has a similar relationship to that we had with Ohm's law. Voltage is equal to current times impedance. So EO is equal to I of S times Z2 of S. The voltage input, however, spans both Z1 and Z2. So it's as if we were looking at this, EI is equal to the drop across Z1 plus the drop across Z2. Another shortcut is to think of Z1 and Z2 as being in series with one another. Therefore, the voltage EI is equal to the impedances summed together, because that's how you combine impedances in series, multiplying the current, which is also I, which is the same as the current through the output. Looking at this, the current I of S cancel, and so our transfer function is equal to Z2 divided by Z1 plus Z2. From the previous slide, we had expressions for Z2 and Z1. So the expression for Z2 was it had a numerator of SL plus R2, and then it had a denominator of CL times S squared plus C R2 times S plus 1. So our transfer function has Z2 in the numerator, and then it has Z1, which again, if you look back on the previous slide, is equal to R1, plus Z2 again, which is the same as the expression that we have in the numerator. S times L plus R2 divided by CL times S squared plus C times R2 times S plus 1. In essence, this is the transfer function, and we could stop here. But in general, we would like to clean up our transfer function a little bit so that it's easier to understand and compare. And so basically, I would like you to get your transfer functions into a form of a polynomial, a single polynomial divided by a single polynomial. So in essence, we want to get rid of these fractions here. And the way that we can do that, the way that we can clear them out, is to multiply through by the denominator. So if we multiply through by this denominator, CL S squared plus CR2S plus 1, do the same thing down here. CL S squared plus CR2S plus 1. Then we can clean this up. So if we distribute this through, this denominator will cancel with that expression. We'll be left with SL plus R2 in the numerator. In the denominator, if we multiply through, this expression will distribute and it'll multiply the R1. And then when we distribute it to the second term, this denominator will cancel with that term, and we'll just be left with SL plus R2. Now this is done. So we've gotten the transfer function, we've reduced it into a form of a single polynomial divided by a single polynomial. We could stop there, or we could distribute the R1 and gather like terms. So I'll go ahead and do that real quickly. Our numerator is SL plus R2. If I distribute this R1, R1 times C times L S squared. If I distribute the R1 to this term, I'll have an S term, and I've also have this S term. So I have C times R1 times R2 plus L, where I factored out the S. And I distribute this R1 times 1, that'll be a constant, and then I'll have this R2, which is a constant. The final form of our transfer function. That may not have seemed very easy, and it may not have been for the first time that you've seen it, but these sorts of approaches for clearing out fractions, clearing out denominators, and gathering like terms and simplifying is something that we'll do with some regularity, so it'll become easier. And it's actually significantly simpler, the algebra that we had to do here, than if we had started from the differential equation, taken the Laplace transform, and then done a bunch of algebra. One thing to be aware of is that this approach is only valid if the initial conditions are 0, as is the assumption when we find a transfer function. Recall that when we derive a transfer function, we make the assumption that we're not including the initial conditions in the model, or we're assuming that the initial conditions are 0. something to think about is to take this circuit that we just analyzed and break it into two, and take a look at, consider it as two loops separately that are in series. So if we look at this half of the equation, you can consider the voltage across the capacitor, as some intermediate voltage. We'll call it EC. So we can think of it as the output of the first loop and the input of the second loop. So in this circuit, EO is the output and EC is the input. And in this case, EC and EO are both the voltage across the capacitor. Therefore, in essence, they're equal. So EO divided by EC is equal to 1. Over here, we can consider this circuit to have an input of EI and an output of EC. So again, transfer functions of the Laplace transform of the output divided by the Laplace transform of the input. This again has the form of a voltage divider. This is like our Z1, and then these two components in series are like our Z2. So the form of a voltage divider, the transfer function of a voltage divider, is Z2 divided by Z1 plus Z2. Z2 we can think of as the sum of these two impedances because these components are in series. So we have the impedance of the inductor plus the impedance of the resistor, that is Z2. And then we divide it by Z1, where Z1 is R1, plus Z2, where Z2 is SL plus R2. If we multiplied these two transfer functions, we would not get the same expression as we had on the previous slide. So this was what we found for the transfer function EO of S divided by EI of S to be. In the past, we had made the assumption that transfer functions of systems in series multiply, but if we multiplied these two transfer functions, we would not get the same expression as we found on the previous slide. So again, previously we had made the assumption that transfer functions in series multiply. So for example, G1 is output over input, it's EC over EI, and G2 is output over input, EO over ES or EC. Typically we treat the ECs as canceling, which should give us the same transfer function that we found originally. But that's not the case. And the reason that is because in circuits, this second loop can load the first loop. In essence, the impedance of the second loop can affect the way that current flows and the dynamics of the first loop. A more perhaps intuitive way to think about this would be to think of two fluid systems in series or two hydraulic systems in series, or even modeling the flow of traffic or something like that. But if you have a system downstream that has an obstruction, or it's been throttled down so that the cross-sectional area is smaller so that not as much water can flow through, or the flow rate is limited, that back pressure is going to affect the system upstream. And so in essence, that's what happens with electrical circuits. And so this assumption that we had made previously doesn't always hold, for example, with circuits or hydraulic systems, etc. So we need to be a little bit careful. One option is to add an isolating amplifier between the two circuits to decouple them so that indeed they are independent, and we can just multiply the transfer functions in series. If we don't have that situation, then we need to consider both circuits or both loops simultaneously. This idea is addressed by some simulation software but not others. In particular, simulation software that is called physical modeling tools, or that actually are aware of what's being modeled. For example, circuit simulators like PSpice or SimPower systems that actually know that what's being modeled is a circuit will take into account this loading effect. However, if we're using a simulation software like Simulink, where we're just modeling the system as transfer functions, but Simulink doesn't know what the transfer functions represent, then it will make the assumption that the transfer functions multiply, even though in reality that doesn't model the system correctly. So this concludes Module 6. We started out the module by discussing the various elements of electrical systems, resistances, capacitances, and inductances. We then learned how to model electrical systems, i.e. circuits, from first principles using Kirchhoff's current law and Kirchhoff's voltage law. In essence, we derived the differential equations governing electrical circuits. We also learned how to model directly in the Laplace domain using complex impedances. In other words, as a way to derive the transfer function model of a circuit. And finally, we talked about the effect of loading when you put electrical circuits in series with one another.